Boom! Yes, folks, so welcome to another video in the series on matrices. This video here is where things could start to get tricky, where things could start to get complicated. This video is where we address the topic of multiplication of matrices. Alright? Excuse. And of course, just as was the case with addition and subtraction, there are certain conditions that must be met before we could multiply two matrices. Alright? Now, whereas in addition and subtraction, you could add any number of matrices as you please. You could subtract any number of matrices as you please. You just go down the line and you apply your arithmetic as you go. With multiplications, generally you multiply two numbers at a time, just like addition or subtraction. So you will hardly ever find in exams a question where you're multiplying, say, three matrices by each other. All right? That is a very, very, very rare event. And in any case, if you have a situation like that, then you have to multiply the first two. Then you multiply, and then you multiply by the last one. So you multiply by the first two, and then you multiply by the last one. The problem with that is that matrix multiplication is not commutative. So for example, if we have matrix A multiplied by matrix B, generally speaking, matrix A by matrix B is not the same thing as matrix B multiplied by matrix A. So that if we have three matrices A, B, C, the order in which you multiply them must be very specific, and usually the context of the question will make that clear. All right? But as I said, this is not something to worry about. Don't go in an exam looking for this. If you get a situation where for some reason you had to multiply three matrices, then you can rest assured that the order of the multiplication will be clear from the context of the question. So for the purposes of our video here, we will stick to the discussion of two matrices being multiplied by each other. So it brings us now to the question of the specific conditions that must be met if we have to multiply two matrices by each other. So again, just to be general, if we have to multiply, say, matrix A by matrix B, so let us say matrix A multiplied by matrix B to give you matrix C. Right? And I put it next to each other because that is generally the notation that we use. We'll say AB equals C or MN equals P or whatever. So usually when you find two matrices being multiplied by each other, whatever letters that they use to denote the respective matrices, they will just put the two letters next to each other. Just as how we have AB equal A multiplied by B, or XY is X multiplied by Y, or 2X is 2 by X, etc., etc. What are the conditions? Well, there is one specific condition that must be satisfied to multiply two matrices. So pay close attention here now. Remember that any matrix that we talk about could be defined in terms of the rank, in terms of the order, in terms of the dimension of the matrix. All right? So this matrix A would be a R by C matrix. All right? A certain number of rows by a certain number of columns. This matrix B would also be R by C as well. All right, so if we want to be a little more specific, we could say RA, rows in A by columns in A, and we could say rows in B by columns in B. So the essential condition for these two matrices to be multiplied by each other is that the number of columns in A must be equal to the number of rows in B. And you could denote that by simply, basically what we do in practice is circle the two to make sure that these two digits are the same. So whatever the number of columns in matrix A is, it must be equal to the number of rows in matrix B. And when we do that, the rank, the order, the dimension of the answer C will be, you take the number of rows in matrix A and the number of columns in matrix B. So this will give you row A multiplied by column B. All right? That will be the order of the answer, big C. This small c, of course, not to be confused with big C. Big C here is the answer you get when you multiply A by B. C is the number of columns in C, number of columns in B, and the number of columns in A. All right? So that is the essential condition that must be satisfied if you have to multiply two matrices. Now, there is a notable exception to this general rule, and I am pretty sure that if we have to delve really deep into it, maybe at the level of university mathematics, we will find that maybe what appears to be an exception is not, in fact, actually an exception. But here is not the place for that. At this point in time, we're dealing up with CSEC, so we don't want to get too far ahead of ourselves if we don't have to. The exception to this general rule is when we mark off the territory here, is when we have to multiply a matrix by a scalar quantity. All right? So, for example, if we have a matrix M, all right, a matrix, all right, M for the general matrix, and we have to multiply a scalar quantity K by M. To get the matrix Km, all we have to do is multiply the constant K by each and every element in the matrix M. So for example, let us say we have a 3 by 2. We use 2 by 3, 2 rows, 3 columns. Let us say we have a matrix M is equal to 4, 0, minus 3, 9, minus 12, 6, right? And we want to find Km. Km in this case will be K multiplied by 4, 0, minus 3, 9, minus 12, 6. And the answer will then be 4K, 0K, minus 3K, 9K, minus 12K, and 6K. All right? Of course, 0K is 0, but we leave the 0 there just for the sake of explanation. All right? Now, let us assign a value to K and use this same matrix just to demonstrate the point. If K is, let me say K is 2, all right? So we're going to rub off here now, right? So if that fellow there is M, then we know that 2M would be, right, 2 by 4, 0, minus 3, 9, minus 12, 6. Yeah? In which case, 2M will be 8, 0, minus 6, 18. All right, let me use this space a little better than that now. 8, 0, minus 6, 18, minus 24, and 12. All right? Right, let me change it up. Let me say we want to find minus 7M. Minus 7M, okay. Minus 7M is equal to minus 7 by 4, 0, minus 3, 9, minus 12, 6, which would be equal to minus 28, 0. Minus 7 by minus 3 is plus 21. Minus 7 by 9 is 9 7s are 63, minus 63. Minus 7 by minus 12 is plus 84. Minus 7 by 6 is minus 42. All right? So multiplying a matrix by a scalar is simply multiplying the matrix, multiplying all the elements in the matrix by the scalar. Now, I want to take this opportunity to warn you fellows, guys and girls, ladies and gentlemen, boys and girls, folks and folksettes, all right? Do not think that this is as simple as an exam question could get. So, for example, you might have a situation, and I'm going to borrow some space on this side. You might have a situation where the scalar might look like this. 2p plus 6 as the scalar, multiply, let me use the same m, 4, 0, minus 3, 9, minus 12, 6. You could get that where the whole of 2p plus 6 is equal to a scalar. So in other words, don't even think about expanding this. Actually, you'll be able to do that, you know. Actually, strangely enough, you could do that. So you get 2p multiplied by all of this, plus 6 multiplied by all of that. You could have a situation like that, right? I'm not going to dabble in that any further. I'm just showing you the kind of thing you could get. All right? So, in other words, the point I'm trying to make here is that when I take my time and explain the concept using a simple scenario, you, as the student, would be very imprudent, which is just a polite way of saying foolish, to assume that that is as far as you're going to get in terms of difficulty level, because that is pretty straightforward. You don't need to make no sort of long stress, no sort of hasikara, as we say in Trinidad and Tobago. All right? You don't need to make any wahala, to use some Nigerian parlance. You don't need to make any trouble over that. That is pretty straightforward. But you might get a question in the exam where the difficulty level, it's based on the same basic concept, but they switch it up a little bit. What are you going to do? So again, I am using this opportunity to encourage you. Go and find questions. Textbook, past papers, find questions and practice. So that when you go in the exam, as far as this topic is concerned, multiplying a matrix by a scalar, no matter how they come, boom, you deal with them. Right, so we're going to continue with our general case now, where we have two matrices being multiplied by each other to produce another matrix. All right, so this is the general situation which you will have at your disposal by virtue of it being recorded on film. You could always rewind, you could take a snapshot. I would encourage you very strongly to take physical manual notes, pen and paper. That will help in your memorization process. So now, what we're going to do is demonstrate the actual workings of this using some tangible examples, thereby setting the platform for you to go on and do further work on your own. So, let us start with a random 2 by 1 and a random 1 by 2. All right? So, if we have a 2 by 1 matrix, let us say there is 2 rows and 1 column. All right? 2 rows and 1 column, let us say 2 minus 3 multiplied by a 1 by 2 minus 1, 4. Now you notice, let me make this point. When you're multiplying two matrices, it is not necessary for the order of the two matrices to be equal. The only thing that needs to be equal, the only situation where something has to be equal to something else, is where, as you just had up in the corner there, the number of columns in matrix A, which is the first matrix, which is the matrix that they're pre-multiplying by the other matrix. You know the vocabulary now, right? And again, I say the order is very important because matrix multiplication is not commutative. AB is not equal to BA. All right? Now that is something you could clearly see if you look. In fact, we will deal with that in a little bit. Right? So the number of columns in matrix A, which is the first matrix, must be equal to the number of rows in the second matrix. Alright? The order doesn't have to be the same. In fact, the only case where the order of the two matrices that I'm multiplying will be the same is if you have two square matrices being multiplied by each other, which we'll do an example of the square matrix in a little bit. Alright? So if you have 2 by 1 by 1 by 2, alright, the order of this is 2 by 1, and this is a 1 by 2. So you could clearly see here that the number of columns in matrix A is equal to the number of rows in matrix B. Which means that the two matrices are, listen to this now, compatible for multiplication. You have to be very specific with the vocabulary now. So normally what we will do, we do that, right? We have verified here that the two matrices are compatible for multiplication, and in so doing, we have now illuminated the order of the answer, which would be a 2 by 2 matrix. Alright? Now I'm going to do some labeling here, and you'll see why I'm doing this in a little bit. So this is row 1. This is row 1. This is row 2. This is column 1. You only have one column here, right? This is row 1. You have column 1 here and column 2. In fact, let me come away from the side of the board because I need the extra space to illustrate what I'm trying to illustrate here. And in so doing, I actually forget. In fact, the actual values are important, so the values could change. Right? And yeah, I'm not going to go back and try to find that now. So let us say again we have the matrices. What's the color I was using? We have the matrix 2, 2 minus 3, and I think it was minus 1, 7, if I'm not mistaken. All right? Right or wrong, we roll in with that. So this is your row 1. Start from the top. This is your row 2. This is your column 1. All right? By the same token, this here is your row 1. This is your column 1. We need more space. We need more space. All right? I need the space here, you know. And you'll see why I need the space just now. So it was minus 1 and 7, all right? Multiply by minus 1 and 7. Minus 1 and 7, which is row 1, column 2. All right? All right. So we have 2 rows by 1 column multiplied by 1 row by 2 column. 2 columns, proper pluralization. We verify that the number of columns in matrix A is equal to the number of rows in matrix B, and therefore these two matrices are compatible for multiplication. So we know therefore that the matrix C, whatever that turns out to be, will be a 2 by 2 matrix. Now how do we get a 2 by 2 matrix? From the combination of a 2 by 1 by a 1 by 2. All right. Well, let me see. Right? Let me see now. All right. All right. So the first thing, and this is a technique that I use with my students all the time. The first thing that you need to be able to do, especially in the early stages, where you're now learning this topic, you need to have a very clear picture in your mind of what the final matrix will look like, even if you don't have the exact values inside the matrix. So for example, we know that the multiplication of this A by this C, by this B, sorry, will give us a matrix C, whose rank, whose order, whose dimension is 2 by 2. So we know that that matrix would look something like this. All right? That is what the matrix would look like. Yeah, I need the space here now. All right? In fact, no, what I'll do, sometimes I'll be kind of particular about how I write these things. It might mean the video probably a little longer than we would normally want it to be. But we go in. Equal to matrix C, 2 by 2. All right? Nice. So in the final matrix, watch it. We have row 1, row 2. You have column 1. I'm using the bottom here now. And column 2. All right? Nice. Now, the quest here now is to fill in the actual values inside the matrix that we get as the answer. And how are we doing that? And this is where this property comes in useful, as you'll see in a little bit. Because this quantity is formed at the intersection of the first row and the first column. This whole thing here is the first row. This whole thing here is the first column. The point of intersection of the both of them will give us this quantity here in the answer. By the same token, this quantity here is formed at the intersection of the first row and the second column. This quantity here is formed by the, is formed at, I have to be very careful here and you'll see why in a bit. It's formed at the intersection of the second row and the first column. This quantity here is formed at the intersection of the second row and the first column. Now, let me start with the one on top. How do we get the value that is located at the intersection of the first row and the first column? Well, we do that, and this is the part where you need to listen now. We do that by interacting, right? Interaction versus intersection. Interacting the first row with the first column. The first row of matrix A and the first column of matrix B will give you the value at the intersection of the first row and the first column of matrix C. Let me run that again. The interaction of the first row of column A with the first column, the first row of matrix A with the first column of matrix B will give you the value that will be located at the intersection of the first row of column C, the first row of matrix C, sorry, and the first column of matrix C. So the first row here is just 2, and the first column here is just 1. 2 multiplied by minus 1, because remember we're multiplying the matrices now, right? 2 multiplied by minus 1 is minus 2. All right, so you put in the answers, minus 2. All right? All right? Excuse me. Right. Similarly, the quantity that will be located at the intersection of the first row and the second column of matrix C will be formed by the interaction between the first row of matrix A and the second column of matrix B. So 2 by 7 is 14. Similarly here, the quantity, the entity that will be formed, that will be located at the intersection of the first row, at the intersection of the second row and the first column of matrix C will be formed by the interaction between the second row of matrix A and the first column of matrix B. So in this case, it will just simply be minus 3 by minus 1. Right? Second row, first column, second row, first column. Minus 3 by minus 1 is 1. It's 3, sorry. Minus 3 by minus 1 is plus 3. And similarly, the quantity that will be located at the intersection of the second row of matrix A and, the second row of matrix C and the second column of matrix C. It will be located at the intersection of those two, will be formed by the interaction between the second row of matrix A and the second column of matrix B. Minus 3 by 7 is still minus 21. That's the 2 by 2 matrix. Yeah? All right. So let us flip the script now. 1 by 2 and 2 by 1. So we had a 2 by 1 by a 1 by 2 to give a 2 by 2. Let me flip the script. How about a 1 by 2 by a 2 by 1? Let me see. So in other words, and I'm going to write the answer kind of small in the corner here because I need this. Right? So AB is equal to minus 2, 14, 3, minus 21. Cool. So how about we use the same two matrices? And instead of AB, let me try BA now. Right. Let me try BA. So BA would be minus 1, 7 and 2 minus 3. Alright? Minus 1, 7 and 2 minus 3. Minus 1, 7, 2 minus 3. Minus 1, 7. So B would be minus 1, 7 multiplied by, multiplied by 2 minus 3. And we rub it off now to get the final answer. Good. So we have now, let me go through the procedure again now. 1 row multiplied by 2 columns here for B. Remember this is BA now. And we have 2 rows multiplied by 1 column for matrix A. So we verify that the number of columns in matrix A is equal to the number of columns in matrix B is equal to the number of rows in matrix A. Remember we switch the order. So in this case, again, just as we had before, we have row 1 here, and then we have column 1 here, and column 2 here. And then in this case, we have row 1, row 2, and we have column 1 here. Just one column, one and only column. Right. So we know that matrix C, the answer will be a 1 by 1 matrix. All right? 1 by 1. So we know now for sure, using these two matrices, that AB is not equal to BA. All right? And we will demonstrate that using 2 by 2 matrices as well. So we know that the answer C will just simply be, watch it, 1 by 1. Remember for the 1 by 1, we tend to use the square brackets, all right? We use the square brackets for the 1 by 1, matter fixed. So how do we get? It's just 1 by 1, one row and one column, right? So let me demonstrate. Don't frighten. You'll see how it materializes now. So this is one row here, and this is one column here. All right? C1 and R1. Yeah? Nice. So the logic is the same as what we did just now. The entity in matrix C, let me call this one, whatever, C is the matrix that we get as the answer, right? We're done using C already. The entity that you get in the answer C, that is located at the intersection of the first row and the first column, will be formed by the interaction between the first row of the matrix B and the first column of the matrix A. Now we realize we only have one row and one column. So what we do? We multiply the corresponding elements in the respective row and column. So the first element in row 1, measuring left to right, by the first element in column 1, measuring up to down. So minus 1 by 2, and then you take the second element. The second element in row 1, multiply by the second element in column 1. And you add those two, and that's how we get the answer here. So in this case, that would be, what is it now? Remember it's a 1 by 1, right? So it will be, let me stick to these square matrices now. All right? It will be minus 1 in brackets by 2 plus 7 by, notice I'm using my brackets, all right, by minus 3. Minus 1 by minus 2 is minus 2 plus minus 21 plus minus 21. Square the brackets, equal minus 2 minus 21. Brackets still square, and the final answer is minus 23. All right? And that is it. So that there is our 1 by 1. So we have AB as a 2 by 2 and BA as a 1 by 1. So using these two matrices alone, it is absolutely clear that AB is not equal to BA. All right? So we're going to pause here, and then we're going to continue with a 2 by 2. One pair of 2 by 2 matrices.